Hi, I'm Drago Anguelov. I lead the research team at Waymo, and I'm here to tell you about some of our recent machine learning research towards autonomous driving systems that scale to the variety of challenges we see on the road. As you probably know, Waymo is Alphabet's self-driving company. We are building the world's most experienced driver and focusing on two categories. So Waymo One is our driving service, and we're moving things with Waymo Via, which is our commercial goods delivery arm. And that includes trucking and local delivery. Since we started as the Google self-driving project back in 2009, we have driven more than 20 million miles on public roads, 15 billion miles in simulation, and in more than 25 cities across the US. In 2018, we launched Waymo One, the world's first commercial self-driving service. And last year, we started ramping up our driverless rides, where no human driver is in the vehicle, for members of our early rider program. So before COVID-19, we were serving up to 2,000 Waymo One and Lyft rides combined per week, and 5 to 10% of those were fully driverless. And the experience goes a bit like this.
That is nuts. It's pretty crazy. It's like there's a ghost at the steering wheel. I kind of feel like royalty being paraded around in this thing.
School zone.
Look at these guys looking over.
Are they?
No driver.
No!
What?
This little Waymo thing is cruising.
Oh, it's a pretty sharp turn. I made it pretty smoothly.
Thank you. Do I say thank you?
We're here. We made it. And I didn't have to drive.
So we're working hard to bring this type of experiences closer to all of you. I'll share a couple of examples of driverless operations. So this is one example of the kind of unprotected left turns that we do in Phoenix. So the speed at these intersections is 45 miles an hour. And we need to carefully judge the time to pass. And so in this case, we decide to wait out for these vehicles and then find the right time to go and execute the turn. Yay. Here is another example I will show you where a vehicle runs a red light while we're trying to make an unprotected left turn.
That's awesome. You see that? That car ran the red, and then our arrow turned green, and it waited for that car to pass.
Oh, wow. That's perfect. That's awesome.
Yeah, so there we go. And our goods delivery effort kicked in 2017 when we started working on Class 8 trucks to see how we can adapt the technology we developed for passenger vehicles to trucks. And we started testing in California, Arizona, and Georgia. And most recently, in early 2020, we partnered with UPS to deliver parcels between the Metro Phoenix stores and the Tempe hub. So here's some examples of driving. Now let's revisit the self-driving problem, right? It's a problem of mapping sensor inputs to steering and acceleration to controls. And at Waymo, we have three sensors, camera, LiDAR, radar, seeing all 360 around the vehicle. And based on the information obtained by the sensors, we need to decide how to act in this environment, right? And so it's a mapping. It's a mapping from inputs of the sensors to controls. And maybe we should use a deep net to do this mapping. Well, in fact, over 30 years ago, there was a seminal system called Alvin that could successfully do lane following based on neural networks. And recently, there has been a lot more interest in such, as they're known, end-to-end approaches. But so far, end-to-end approaches have not been able to match the quality of the production self-driving systems that are being developed by the leading companies. And so to understand what makes that problem difficult, it is perhaps instructive to compare it to the game of Go, where there has been dramatic successes by models such as AlphaGo and AlphaZero by DeepMind, which obtained superhuman performance in this 1,000-year-old game. And that was incredibly impressive and a big milestone for AI. So when studying, though, this domain, something that comes out is that Go is a game of simple inputs. It has very elegant, simple rules. The game is deterministic. And it has fairly complex output because it has close to 400 positions you can put a stone. Now, in contrast, our domain has extremely complex input. We have millions of pixels. We have lots, LiDAR and radar scans. We have a complex environment where, with complex agents such as humans that act in unpredictable ways in many ways. And now we also have a fairly simple output. So the goal is to generate a 2D trajectory on the road. And so there's somewhat different problems, all right? And let's dig a bit more into ours. First of all, in terms of environment complexity, factors a lot in the input complexity. So we have different weather, different seasons, different times of day that we need to handle. We have complex scenes with a lot of scene context that matters and determines behavior of the agents in the scene. So here, in order to progress, you need to understand traffic lights, you need to understand sidewalks. You also need to understand that people can be opportunistic. And then when you're still not going, other vehicles can start getting opportunistic. And so we're slowly making our way through this intersection. Now, of course, there's a second set of pedestrians that we need to make progress through. And so that's a scene in San Francisco. I live not so far from here, and it's all very familiar. Eventually, though, here we are making progress safely along the road. But this illustrates the need to really understand the scene configuration and agent interactions in order to be able to drive well. And another aspect that makes driving difficult is that there is a lot of events that happen quite rarely, maybe once in 100,000 miles. Some happen in millions of miles. And this cat, for example, running from behind the car, it's not too common of an occurrence, and it needs to be handled safely. I'm happy to report in this case, both the cat and the vehicle driver, everyone came out perfectly fine from this encounter, right? And last but not least, so in games of Go, or in some of our reinforcement learning work being done by the machine learning community, in many of those, you can learn by trial and error. So in Go, you can lose millions to tens of millions of games, and of course, improve as a result. And in our domain, we cannot drive unsafe in the real world. We need safe operation at all times. We need to ensure the safety of the public. And so that adds a level of complexity that is important and needs to be handled. And so what do people do, right? To be able to handle the issues just described, so modern autonomous stacks have a modular design. And they consist of standard building blocks, such as perception, behavior prediction, and planner modules. And so as data flows through the system modules, there are several key trends. So we go from high-dimensional camera pixels and LiDAR and radar scans to a more compact and structured environment in representation in the form of objects, their trajectories, and relationships. And we also go from sensor readings in perspective view, this can be the camera images, this can be the range images and the LiDAR, to top-down Euclidean view, where it's easier to generalize. So additional hierarchical structure is typically encoded also in the vehicle planner in order to be able to make effectively both long and short-term decisions. So the router selects a long-term route, the high-level route that we want to execute, and then the planner generates trajectories that safely make progress along the route, and the controller executes these trajectories. Typically, earlier modules in the stack leverage supervised learning. And supervised learning is very helpful in coming up with the object-oriented representations and the relationships that are useful for planning and predictions. However, in planning, we when we select actions and execute them, we also affect the environment. And evaluation of decisions requires closed-loop execution of a policy over longer time horizons. And as a result, purely supervised techniques are limited in Planner, and we need to do things also like reinforcement learning, imitation learning, cost function learning, and more sophisticated evaluation, often in simulators. So that's great. So we have a modular system, right? And a modular system, as the one I described, has been key to getting good performance in our domain because it's designed to capture key intuitions and structure from the environment. So in other words, it's embedding a key inductive bias into the model. And also allows modular setup allows an engineering team to make parallel progress on multiple tasks. One potential drawback, though, with pure modular development is that engineers design the interfaces between the modules, and those interfaces typically only pass information that the engineers consider relevant. Also, each module is typically evolved separately. It does not necessarily optimize directly the objectives of the module downstream. And so one exciting direction of ML research is to build neural network which still remains modular in nature. So it produces intermediate outputs that we can understand. And it also, this network encodes in their design the intuitions and structure from the domain. And those intuitions are the ones I just described before. So going from perspective to top-down view, going from sensor readings to reasoning about objects and interactions. These networks can be trained to do well on multiple tasks across the stack, and their design can be guided by our intuitions about the domain still, right? So we're trying to embedding some of these intuitions that went into the modular design in the networks themselves. And there's an interesting, exciting research areas how far you can go with this approach. And I will tell you about some of the recent work that we did at Waymo Research and we published in this direction. So one work of ours is on StNet. It's a CVPR paper on simultaneous detection, tracking, and prediction with a model that tries to capture some of the intuitions I just talked about. So what does this model do? So you start with the lighter point clouds from several time steps, and we process them with the backbone neural network, computing features. And now we fuse these features across time. Now we want to produce detections and tracks. And the way we do it is we have a proposal generation phase where for each anchor, we not only predict whether there is a bounding box of an object in that location and shape, but we also do other temporal anchor proposals. So we also predict where the object was in the past, in the past frames. So for each anchor, we predict several boxes over time. And we do this for all anchors. And so one interesting property that this allows is now that we can, because we know how each object evolves over time, we can extract more sophisticated features. And so some examples of these features are, well, we have the boxes in all the time slices, so we can just pull out the embeddings associated with these pedestrians, or we can potentially even pull the point clouds associated with them, and extract features for each frame that capture the shape of and the pose of this pedestrian, for example. We can also capture a global appearance feature, which is over the whole region of pedestrian motion. And this tells you a lot about how the point cloud changed as the pedestrian moved. So it contains a lot of motion information. And things we can also do is we can just extract the history path because we have all these anchors and we know their correspondences. So we know how the object is moving in the first place. So we can take all these features and extract them, concatenate them. And so now we have our rich features for all the objects. And now what we can do is we can model their interactions with the graph neural network. And so this graph neural network passes information across all these objects that were detected and their features, and the results in the final predictions for the model. So what are the results of such a model? So compared to a multiple view fusion work of ours about a year ago, which uses a single lidar spin, StNet improves significantly the object detection, but most of the gains are just due to stacking frames. And you can do this you can see the comparison to IntentNet, which mostly stacks frames, our implementation of IntentNet. And so this additional structure at the end is fairly marginal for the detection task. But it seems very crucial for high accuracy prediction tasks. So especially for prediction, and especially for fast-moving objects, this additional structure and these additional features we can extract in the network in the later stages yields very significant gains and improves predictions notably. And so that's an interesting result. So as we go more towards behavior prediction and planning, these types of representations really matter. And so there is also a question, okay, so we talked about modeling interactions between agents. What about the map? And so here I will describe our work on VectorNet. It's our also CVPR paper on structured scene context encoding. And so how do people normally encode the map? Well, they take the map content and they render it into an image with many channels typically, and then apply a convolutional neural net because that we know how to process images well. Now that works okay, but it's first of all costly because you produce these large images at long ranges. To understand the context of a scene, usually you need fairly large map. Also, you often take continuous data from mapping in the form of vectors and curves, or potentially reconstruct it online by your algorithms. And you then would quantize it into pixels, and that's lossy. And last but not least, convolutional neural nets are not really good at modeling long-term structure in the environment because they're made up of small kernels, and then you need many layers for the information over long distances to propagate and cross-correlate. And so our approach instead models the structured information in the map as polylines. And so the map and agents is simplified either as points, such as stop signs and agents, polygons, such as a crosswalk, or curves, like the lane boundaries. And all of those are piecewise linear polylines. And we can process the polylines, and for each of them, we can have a little network block that computes essentially features on these polyline subgraphs. And then we can model the interaction between all the features in the map using a global interaction graph that shares this information, and that's implemented as self-attention transformer layer, right? And that allows us to reason to incorporate all this information when we do our predictions. And so this global interaction graph there is trained with two losses. So one of them is, of course, we want trajectory prediction loss, L1. But the other one is interesting because we have transformer networks, we can do map completion loss, so we can force the model to complete features in the map. So we can mask them out and ask the model to complete, to reconstruct them. And that adds additional structured loss that helps in the models in the prediction. And so how does this work? So compared to the CNN alternatives, ResNet 18 model based on top of image rendering, we get significantly better performance in prediction for a fraction of the parameters and a fraction of the compute, which is quite exciting. And at the time when we did these experiments, we were first on the leaderboard in Argoverse on prediction for pose in 3 seconds. That was around March, and of course, behavior prediction is a really hot field, and there's a ton of really good work. And so I'm sure by now, as you can see in this workshop, actually, the state of the art has moved even further. Our state of the art is also quite exciting, and I look forward to sharing it with you in upcoming conferences. So far I shared with you some vision and some work towards this vision on developing more end-to-end models for perception tasks and prediction and potentially planning. Now, to support such research on autonomous driving topics, we have worked on releasing and compiling the Waymo Open Dataset, which is a large and high-quality dataset that we shared with the research community. And I will give a brief update on this dataset today. So as of June 2020, we have close to 2,000 segments at 10 Hertz with 5 LiDAR, 1 mid-range and 4 short-range, and 5 high-resolution cameras with really great synchronization between the two, with more than 10 million 3D boxes and more than 10 million 2D boxes. So this data set is very diverse. It has data from San Francisco, Phoenix, and Mountain View. it has all kinds of conditions and situations and construction and so on, right? And so it's very ripe for autonomous driving research. And so we have already had 3 releases. We initially released 1,020-second segments with 3D labels, and part of them annotated with 2D labels. And now, later we released the full set of 2D labels, and now in March this year, we released a 150-segment test set that we use for open dataset challenges, which we will talk about shortly. And we released an 800-segment domain adaptation set that's partially 3D labeled, partially unlabeled for one of our challenges. And so speaking of challenges, we launched 5 challenges in mid-March. And it was a competition with prizes. The tasks are 2D detection and tracking, 3D detection and tracking, domain adaptation, which is take data from, mostly labeled data from San Francisco, Phoenix, and Mountain View, and a little bit of labeled data from Kirkland, Washington, and some unlabeled data. Try to do well on a new city in rainy conditions, which have very different properties and significant domain gap, as we found. And so this workshop already happened on the Waymo Open Dataset challenges at this CVPR. If you're interested, please check out the webpage. There's a lot of exciting talks. There's a lot of very strong results. So we have a lot of competition winners presenting, and you can see the kind of work they did that really increases the quality of results on our data set. One thing we do is we continue keeping our leaderboards open, so new submissions can keep being evaluated against the state of the art in the field. So with regards to the challenges, we had very robust participation, 165 teams from industry and academia, 100 unique entries on the leaderboards, and over 2,000 evaluations against our validation sets, which is really exciting, right? And so again, I invite you to check them out. It was very exciting for us to see what people could come up with. It's a great, fantastic community. And so far, as you can see, these challenges were focused on detection and tracking. But now I will present you some other exciting work that can leverage the Waymo data and the Waymo Open Dataset beyond tracking and detection. So one of the things we've been working on is deep structure from motion. So that's a research framework covering scene geometry, semantics, and dynamics. And it's a collaboration with Google Brain team with Anelia Anguelov and Ariel Gordon. So what is structure from motion framework? Typically, the idea there is to learn 3D geometry from image sequences by exploiting motion parallax. And in the deep frameworks, typically, they warp images in time and apply per pixel losses as supervision signals. And this way, they can, without too much labeling, they can reconstruct a rich 3D structure in the environment. And there's a lot of reasonably successful methods. And a lot of them work like this. So if you have a pair of images from a video, typically, you can learn a depth estimator model that provides the depth per pixel. And this, in our data set, actually, you can train it with LiDAR, which is really great. It improves the quality significantly. Then, what you also can do from this pair of images is you can estimate the ego motion between the two and potentially any residual flow for the moving objects in the scene. And so armed with all this information, what you can do is, given the depth and the flow and the initial image, you can generate novel views in the scene. And these novel views now can be for the next frame. So at the time of t+1, you can generate how you think the world would look then based on time t. And if this is your reconstruction, now you can apply photometric consistency or other consistency losses to the actual image. And this can help train your models, the blue boxes. So what a characteristic of our deep structure from motion system. First of all, we paid really strong attention on handling rolling shutter in our environment. And the Open Dataset has the provided shutter timings, which make it possible. And we find that this is quite important because the vehicles are moving fast, and properly correcting for the projective geometry avoids artifacts and errors at higher speeds. Another thing we do is we train on multiple images and cameras simultaneously. And what we find is that by training on 5 cameras, each individual camera improves significantly by 6% or more the quality of the depth estimation. And the other thing that we can do And this is one of the great properties of the Waymo Open Dataset is we have a ton of data. We have hundreds of thousands of scans and even more images associated with those. And so you can train really high quality models. And of course, internally at Waymo, we can have orders of magnitude more data and train even yet higher quality models. And so this is the differential view synthesis that I was talking about that allows you to, when we take the depths from our estimated from our images, this allows us to just move the camera in this reconstructed 3D world, and you can see that we can create very nice looking views around the initial view. And so what can you do with these VIDAR models? Well, first of all, you can have state-of-the-art camera-centric models for depth, motion, dynamics. And also, it's very valuable as a consistency modeling framework. So if you have semantic models, you can try to improve them on unlabeled data with fairly low integration effort, because now the VIDAR framework, the structure for motion, it gives you correspondences across time. And you can say, hey, this pixel on the vehicle at time t is still a vehicle at time t+1. And now you can have a loss, and you can push gradients through your net and improve it. So a bit more on that later. But this is an example of our model in San Francisco, estimating depth from camera. And you can see it's quite high quality. The edges are crisp. Thin objects are modeled well. And we support all the 5 cameras. What's exciting is if you look, in very shady areas, the model does not have a problem doing a good job. Or there's a case here on the bottom left where there is some water on the camera. And even this way, the model is still fairly confident that in the shape of the tree behind. In the middle, that's a rainy weather and reasonably dark. And it still does a good job of seeing the vehicles all around. And so we get very high quality depth. Another thing we can get is 3D flow. So this is 3D flow estimated by our model. This is learned in an unsupervised way. The boxes were not used. They're just detector output. And so here you can see the flow color coded. If it's more orange, you're moving to the left. If it's green, you're moving to the right. And this is just reconstructed by our models. Well, I mentioned the use of VIDAR as a consistency modeling framework, so I'll say a couple words more. So typically, say you're training semantic models that can be panoptic segmentation, it can be object detection, it can be any other type of perception model. You have some labeled data, and you can train it with supervised loss, but you have a lot more unlabeled data. And a framework like VIDAR allows you to train your model with an additional loss. And the way it works is like this. You have an image at time t, and you can predict, say, the semantic segmentation of that image into vehicle, non-vehicle. And now you can use VIDAR to generate essentially the semantic image at time t+1 via the depth and the flow and the motion. And so now you can add a consistency loss in the semantics. You can say, hey, this pixel is still a car in both of these images. It should be consistent. And when you do things like this, we, for example, published a paper jointly with the Google Brain team, doing this on semantic segmentation with just Coco and cityscapes. So we managed to show that just adding unlabeled training based on consistency on a data set like cityscapes can improve Coco, despite the major domain gap between these two data sets. And now there's a lot of ongoing work to apply this type of ideas to our internal data sets in our domain, which is very exciting. Another exciting application that one can experiment with the open data set is data-driven sensor synthesis. And so this generally is inspired by the fact that we talked about, is that to test a planner, you need to be able to play out longer-term scenarios and see whether this behavior resulted in good or bad outcomes. And now, to do this, you need to develop and test behavior models in simulated environments. And especially if your models are more end-to-end, that's generally, you want this scenario replayed with realistic sensors in the loop. But how do you get these realistic sensors in the loop? So we have some work at this conference as well called Surfel GAN. Traditionally, what people do is they generate synthetic data on top of a game engine such as Unreal. And that requires significant manual effort. It can require artists, designers, may require collecting a bunch of assets and modeling material properties. And even then, there can be a significant domain gap between the synthesized environment and the real environment, because your sensors actually may have different properties than what you did in the simulator, right? You did not create the simulator data out of your sensors, ultimately. And so our idea in Surfel GAN is to reconstruct the environment in vehicles using our own sensors, LiDAR and camera. And then, based on this reconstruction, now we can render novel vehicle configurations and simulate sensor based on this reconstructed configurations. But of course, those may have artifacts or problems, and then we use a GAN model to fix this domain gap and to bridge it between synthetic and real data. So I'll tell you in a little more detail what we did. So to reconstruct the scene, we use Surfels. And Surfel is a disk in 3D space. Multiple Surfels together approximate arbitrary 3D surface shapes. Now, the problem with the Surfel is, especially if you assign a single color per Surfel, is they can lack detailed texture information. So there's a fundamental trade-off between size of Surfel and stability of geometry and how much appearance you can store. That's not a good trade-off. And so instead, what we did is we enhanced the Surfel with texture from the camera at much higher resolution. And we also store a codebook of Surfels based on distance, because in some cases you may approach certain objects much closer than others. And ideally, you would have a more realistic reconstruction if you maintain the resolution properly. And so here's an example of our reconstruction. So on the left is a real log image. In the middle is the baseline Surfel reconstruction, which uses a single color per Surfel. And on the right is our texture-enhanced Surfel. And you can see that already it looks quite realistic. That said, there's still some gap, because you can have artifacts on occlusion. You can have missing parts of the scene. You can also, again, approach certain objects much closer than initially in the real world. And so you want to apply an additional GAN model to rectify this Surfel rendering. And so then it becomes an image translation problem. You go from an image generated from our 3D reconstruction to a final image. And one interesting fact in our case is that we actually have two types of data easily available. So the first one is paired data. So we can use the reconstructed scene along with the camera poses, and we can get corresponding images for those from the real camera data. And so, and the second one is we could generate, we can pick arbitrary real data images, and of course, unpaired. We can also render arbitrary views in our Surfel reconstruction. And we could try to push those to look both as similar as possible after the network has done the mapping. And so our final model is a cycle GAN. It contains two symmetric image generators and discriminators. Our training loss consists of three terms. The first term aligns the prediction with the ground truth data in two directions and applies to paired data. So then you're pushing the reconstruction, the post-network image to look like the real image directly. You can just supervise it. And the last two terms apply to both paired data and unpaired data. And they can include the adversarial term and the cycle consistency term. And so when you train this, what do you get? So first of all, you get novel view rendering. So on the left, you can see the closest logged image in our actual runs segments. And then we chose a novel, which we did not have in the real world. And we render it with using our Surfel reconstruction. And then we apply our GAN, and the result is visible on the right? And you can see that the GAN fixes certain artifacts and cleans up the image significantly, makes it look more realistic. You can do something else, which is novel scene configuration modeling. And so on the left was a reconstruction we had of the real world. And now we pulled out the vehicle further up, or like we rotated the vehicle on the bottom some amount. And so that's the rendering. And then you can see that the Surfel GAN significantly, again, improves the rendering on top of that. And so it allows us to render new scenes that we have not done before, even with cameras. And so, of course, there is still a question. These are qualitative examples, and it would be good to see a more quantitative measure of how do you improve in realism. And for this, I refer you to the paper. We have a lot of experiments, both on realism and how much we can reproduce detection results and other tests that I refer you to the paper. So this concludes my talk. Thank you for watching, and please stay tuned for more exciting research from Waymo and updates on the Waymo Open Dataset.